Okay, so I want to pick back up with the thought about strong versus weak acids. So we're still here on guided notes. We're at the bottom of page 2, and I've got a couple of diagrams. And so there's just a few things I want to discuss with this, and then I'm going to talk about the last little bit of stuff, neutralization, and just a touch about titrations, and then I want to leave any of the actual math problems for in class. Okay? All right, so just a few examples of strong acids. Hydrochloric acid is considered a strong acid, hydroiodic acid, sulfuric acid, and nitric acid. Those are all strong acids. What's the difference between a strong and weak acid? The difference is how many H pluses form whenever they're in solution. The more H pluses that are available, then the stronger the acid. So if we look here on the left at hydrochloric acid, you can see here that we are signifying the hydronium ion by these H3O pluses. There's a large number of those here in the hydrochloric acid. As a matter of fact, almost every one of those dissociated into H plus and H3O plus and Cl minus. On the other hand, if we look over here at acetic acid, we can see here now acetic acid is a very weak acid. Notice, look at how many of these acetic acid molecules are still fully intact. And you can see here out of this representation that only one out of those representing this portion of the solution dissociate into H3O plus and then the acetate ion. So a weak acid produces much fewer of the H pluses, so you're higher on the scale towards 7, whereas something like HCl produces a greater amount of H3O pluses in solution, and so therefore it's pushing itself closer to that 0 mark as a pH. Strong bases, the same idea, okay? So a couple of examples of really strong bases are sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. A strong base almost completely ionizes into its component pieces. Here on the left, we have sodium hydroxide. It is breaking apart into almost all NAs and OH-, which is going to push its pH closer to 14. Where, as an example of a weak base, ammonia, most of its particles exist in the solution as a molecule, not as charged particles. So we can see here, of all the particles here inside of this solution, that we have a greater number of ammonia molecules still intact, with very few that will dissociate into charged particles. Okay? So weak base on the right, strong base on the left. Now neutralization. So this is really, our whole goal is to talk about neutralization. So neutralization, and guys, just so you're aware, it's kind of like we're skipping over to page 4 on the guided notes. The information is here for you. I just wanted to show you where it was located. Okay? But in acid-base reactions, actually what happens is that the acid and base react together to create neutral products. Salt and water are the general products that are formed in neutralization reactions. So hydrochloric acid and sodium hydroxide together create sodium chloride and water. That is it's neutralized at this point. You're taking two things that are strong and can be potentially dangerous, and you're turning them into things that are neutral in nature. So in neutralization, so the acid, we already know, we've talked about this, that it produces the H plus ions when dissolved in water, and the base produces hydroxide ions when dissolved in water. A salt is an ionic compound made up of the cation and anion from the acid-base reaction and neutralization. Oh, well, that showed up last, didn't it? Excuse me, y'all. Oh, and you know what? I actually want to talk about this tomorrow with you. I'm so sorry. So now I'm going to skip around here to another PowerPoint, and we're going to talk just for a second about titrations. So that would be right here on page 3 of your guided notes. So I just want to go over some of the terms. A titration is where we take items, these burettes, okay, the pictures on your left, and we control the amount of each item that we're adding to our container to generate a chemical reaction that in the end creates an equilibrium between both of the reactants. So basically titrations are the controlled addition and measuring the amount of a solution of known concentration that is required to react with a measured amount of a solution of unknown concentration. So the other thing about titrations is that we know something about one of the items. Like say the one on the left here, this blue solution, we might know its concentration specifically. It could be 2.0 molar HCl. And we're going to titrate it against something that we know it's a base, and we know the identity, so it could be sodium hydroxide. We just don't know the concentration of that. And we can react those two together in a proportion that will allow me to do some math to go ahead and figure out some mathematical information about the unknown solution on the right. So just a few terms that are going to be important for you are the terms standard solution. When I say standard solution, I'm referencing the solution that I know information about. It's the one that I know numerical concentration of it. An example of that would be 2.0 molar HCl. Indicators, which you've worked with before, are basically weak acids and bases that are sensitive to pH changes, and they will change color within a range to let you know some information about your reaction. What are they trying to tell you about your reaction? Those indicators are letting us know something about our equivalence point. You did those little mini ones in your well plates where you were waiting for that color change to occur. It might have been hot pink, it went to light pink, and then it disappeared. Whenever the color change occurs, we're at what's called the equivalence point. And the equivalence point is the point at which two solutions that are used and titrated against each other, they're both present in equivalent amounts within the container that you're reacting them. And we also call that the end point, is what we generally. So the equivalence point, you might also hear me talk about it in the language of the equivalence point. Okay? And so it's basically telling us that the moles of our acid is equivalent to the moles of our base, and we are done with our reaction. Okay, we'll pick up together as a class. Thank you so much.